Welcome, everyone. I'm thrilled to have you with us today as we explore how simulation, engineering, and hands-on learning come together to inspire the next generation of problem solvers. Today's session highlights a growing collaboration between TryEngineering, MathWorks, and IEEE Signal Processing, three communities deeply committed to empowering learners and educators. I'm Donna Schultz. I'm the Senior STEM Education Manager here at IEEE. And before we get started, I want to do a few quick housekeeping notes. You're invited to use the chat to share ideas and questions throughout the session. We'll pause for Q&A at the end of the webinar. The slides and the replay link will be shared after the session concludes. But for now, I want you to take a quick minute to check out the poll and tell us who you are. Great, I see people in there. Super. All right, I thank you for those who have voted. We really appreciate that. It was great to see who's joining us today so we can customize for you. I'd like to begin by introducing our partners at MathWorks. MathWorks, founded in 1984, MathWorks is the creator of MATLAB, a powerful environment for numerical computation, data visualization, and algorithm development, and Simulink, a block diagram environment used for model-based design of engineered systems. Engineers and scientists worldwide rely on these tools to design, test, and improve technologies we depend on every day, from automotive and aerospace systems to communications, energy, and healthcare. More than 6,500 educational institutions use MATLAB and Simulink as foundational tools for teaching engineering principles and accelerating scientific discovery. Their commitment to education is a key reason this partnership is so impactful. We're also proud to collaborate with the IEEE Signal Processing Society, a global leader in advancing the science and application of signal processing. Their expertise helps us connect classroom learning to real-world technologies, from audio and image processing to communications, sensors, and emerging AI-driven systems. So together, IEEE TryEngineering, MathWorks, and IEEE Signal Processing are working to expand access to engineering education by developing lessons and activities that show how simulations and signal processing concepts have solved real-world challenges. Today's session is part of that shared mission, and we are excited to explore it with you. Our agenda today, we're going to do some introductions of our experts, our partners. Then we'll go through the Brightbeats lesson overview and demo. We'll do a simulation overview and demo, and then we'll close with that Q&A that I mentioned. So I am thrilled to introduce our speakers for today's session. Dr. Kathy Zhang is a STEM outreach engineer at MathWorks. After obtaining a PhD in neuroscience from Yale University, she gained expertise in evidence-based teaching practices and student persistence in STEM as an education research scientist and college instructor in biology and neuroscience. At MathWorks, Kathy leverages her research and teaching experience to scale global primary and secondary school initiatives in engineering and computer science, fostering interest and retention to prepare the future STEM workforce. So welcome, Kathy. I'm also going to introduce Martin Ferrara, is a microbit champion and STEM director at Hans Christian Andersen School and High School in Uruguay. With a background in physics education and electrical engineering, he has developed expertise in hands-on STEM learning, microcontroller-based experimentation, and project-based methodologies. In his role, Martin leads interdisciplinary STEM initiatives that integrate microbit, engineering design, and real-world problem solving, empowering students to become creative, confident, and socially engaged innovators. Now, Kathy will take it from here, introducing us to the power of MathWorks. Kathy?
Thank you so much, Donna, for the super kind introduction. I'm really excited to be here today. Donna did a great job of introducing MathWorks, but I wanted to take a moment to tell you a little bit more about MathWorks, our products, and our customers. So MathWorks is the leading developer of mathematical computing software. Engineers and scientists worldwide rely on our products to accelerate the pace of discovery, innovation, and development. Our software is used to design, simulate, and test many of the products we rely on every day, like the car that you drive, the plane you're going to fly on for your next big trip, your smartphone, even your washing machine. We like to say that if it moves or measures, it's likely that our software was used in its development. We created MATLAB and Simulink to help engineers and scientists do their best work. MATLAB is a programming environment for algorithm development, data analysis, visualization, and numeric computation. And Simulink is a block diagram environment for simulation and model-based designs of multi-domain and embedded engineering systems. With Simulink, engineers can design, simulate, and test systems before moving to hardware. Millions of engineers and scientists worldwide use MATLAB and Simulink. In fact, there are over 5 million users of our products in over 180 countries, including at all the top automotive and aerospace companies. Altogether, our software is used at over 100,000 businesses, governments, and universities around the world. To accelerate the pace of engineering and science, we're also deeply committed to education. Our software is taught at over 6,500 colleges and universities around the world, and over 2,300 of these schools provide MATLAB and Simulink to everyone on campus. There are over 2,500 MATLAB and Simulink-based books available in 27 languages. And we're proud to say that each year, tens of thousands of new graduates enter the workforce with MATLAB and Simulink skills and experience. Our passion for educating and inspiring the next generation of scientists and engineers is why we're so thrilled to be collaborating with IEEE TryEngineering to bring our tools and STEM education to a global community of primary and secondary school educators. Our newly published collection page includes information about how to access our software, resources for students and educators to learn how to code and use MATLAB, as well as a collection of featured lesson plans that are suitable for middle and high school students and teachers. I want to take a second to highlight a few of the resources on the collection page. First, there's a section that helps you gain access to MATLAB. Once you create a MathWorks account, you can open MATLAB online directly from your browser by visiting matlab.mathworks.com. This is free to use for up to 20 hours a month and provides 5 gigabytes of MATLAB drive storage. If you're interested in using MATLAB in your schools or for your STEM outreach program, we encourage you to visit our website to learn more about other license options. Next, we have a few resources to help you and your students familiarize yourself with the tools. This includes Learn to Code, MATLAB On-Ramp, and Simulink On-Ramp. These are self-paced interactive tutorials that are designed for brand new users and are free to access by anyone. We also have a vast library of tutorials, cheat sheets, examples, and how-to videos designed for beginners and students on our YouTube channel and student GitHub page. At the bottom of this collection page, we've included a small collection of featured lessons that showcase the power of MATLAB for simulation and modeling engineering designs. These lessons were developed in partnership with curriculum development organizations, Youth Engineering Solutions, and Engineering for Us All, to help bring computational thinking and hands-on engineering products to middle and high school students. Finally, our collection page spotlights the Bright Beats Challenge, which we'll be demoing today. This is a two-part lesson plan that we've developed in partnership with IEEE Signal Processing Society to introduce middle and high school students to signal processing. In this activity, students will be transforming visual signals into audio signals in two ways. First, they'll build a physical device that uses a microbit to transform ambient light and black and white images into sounds. Then, in an accompanying MATLAB activity, students will turn pixels from digital images into piano notes. By the end of this activity, students will have gained hands-on experience in engineering design, transforming and analyzing different types of signals, and applying different signal processing techniques. To provide you with an overview of the first part of this activity, the Engineering Design Challenge, I'm now going to turn it over to Martin.
Well, thank you, Katie. Well, this TryEngineering lesson is organized in a clear and teacher-friendly structure that guides both instruction and student learning. It begins with the learning outcomes, which define what the students should achieve by the end of the lesson. The lesson plan presentations help teachers to introduce the topic and engage students, while materials and preparation ensure the activity is being practical and ready to implement in the classroom. At the center of the lesson, in the Engineering Design Challenge, is where the students face a real-world problem that motivates a hands-on learning. When here in the activity instructions and in the engineering design process, the students have a step-by-step solution as they plan, build, test, and improve their design, encouraging engineering thinking. Supporting sections like background concepts and vocabulary provide a scientific foundation in key terminology. And finally, you have some student worksheets or curriculum alignment and related engineering fields to connect the activity to the assessment. So you can connect with the educational standards and engineering careers. I mean, this structure makes the lesson engaging and structured and strongly connected to real world engineering. So to understand this activity, we briefly go through the steps online in the lesson so everyone can clearly follow the guidance on this practice. First, the students are introduced into the challenge and work in teams to explore how sound and light can interact. They plan and build their initial design using the available materials, focusing on creativity and problem solving rather than getting a perfect result. After that, the students will test their designs, observe what works and what does not, and make improvements based on their results. Throughout the activity, the teacher acts as a facilitator, encouraging discussion, experimentation, and reflection. That's important. So this step-by-step structure helps the students to stay focused, collaborate effectively, and experience the engineering design process in a hands-on and engaging way. So let's go to this topic that we are working today. So we start showing an image of real sample of Braille, asking the student if they don't know what it is. So this goes into step 1 of the guide. And then we ask them if they know what it is, who used Braille, and what it's used for. It opens a short discussion about accessibility and how information can be communicated through senses other than sight. Then you can watch a short video. It's the incredible story of the boy who invented Braille. It's a short video, like 3 minutes, that will help the students to understand the human and innovative side of the system. When they connect the idea directly to the challenge, it's something similar to Braille. So this idea of Braille challenge will help, for example, impaired users to read an image using sound. So we will use the microbit to transduce light and dark areas of a black and white image to be translated into musical tones, creating a sensory bridge that covers light, that converts the light into sound. Okay, so in the second step that we have in the design challenge, students will read the full design challenge together, and then we will discuss the criteria that will define what is a successful solution and what they should achieve. It will have some constraints, for example, the available materials, the time, or technical limitations. This will help the students to understand the problem clearly and set realistic goals to design within the real world conditions. So let's go here. So let's go to the Brightbits challenge slide. There. Here. Can we see the slide? Or okay. We are working on it. We are not seeing the slide here. So there. The Brightbit challenge, the students, as I told you, they will a simple device using the microbit that will react to light. So the key idea here is to transduce different light level into different sound levels, like musical notes. So they will hear the image itself. That's something that has to be clear here. So you will be translating a visual information, a visual signal, into an audio signal. So at the same time, they will be learning about sensors, data translation, and a creative problem solving. So we discussed about the criteria and the constraints. So we can go further into step 3. There. So in this step, students will work with a high contrast black and white image. So they will cut into strips that image, as you can see clearly there. And then these strips will slowly move across the microbit-like sensors. Each strip passes over the sensor. The microbit detects changes between light and dark areas. Those changes are immediately translated into musical tones, so the image is not seen but heard. This allows the students to experience how visual information can be transformed into sound. So let's go to the next slide to see how you can prepare the image. Here you can see a 7-year-old student that prepared the image into strips. So he will draw the image. The important thing here is there has to be a high contrast image using black and white patterns that create something clearly distinguishable. At the same time, the design should be homogeneous, avoiding large areas, as you can see there, are completely white or completely black. You have to leave no big empty spaces, so as the sensor can measure that light going through the design. So they will help the sensor to detect smooth changes in the light. So in step 4, what you can see is the main challenge. So here is where students start to make some code in MakeCode platform from Microsoft. This platform is used for programming. So the microbit will be programming the display to show the light level on the screen, and so they will see how the sensor works. So we will shine a flashlight into the microbit and see some changes. So we will also open the serial monitor to observe light and data changes in real time. And with this simple activity, will understand the behavior. They will understand the behavior of the device. So here we are seeing that there are a lot of people that never use at least 3 people, or that never use the microbit. Oh, that's something. Well, we can show you how to use it. Okay, there's a lot of people there that never use the microbit. Well, it's a project that was developed by the BBC of London and and Microsoft. It's a small device. I have one right here. Oh, here it is. This is the small device here. It's a small board designed for students, little ones, teenagers. Everyone can use it. Has a lot of built-in sensors in it. And well, it's a beautiful board for students and it's very cheap. I mean, it's raw. This one is raw and it's the second version of it. Yeah, has a lot of sensors, has magnetic sensors. Actually, the new version has a built-in microphone, radio frequency stuff that you can play with. I don't know what else, but you can measure magnetic fields. It's a pretty tough board for small ones. Well, we can go and see how to program it. So here, what we are seeing is the environment of programming the microbit. That's called MakeCode. So we will download. First of all, we need to connect to the computer and download the program as an X file, or you can download it directly from this page. Once the program is installed, the microbit starts displaying the light level and by sensors, like we define in the code. As you can see there, you can see some serial write number from a light level sensor. You can explore the serial monitor there, showing real-time data going through the device connected to the computer. So when there's some light, it goes to 255, and when there is no light, you can see it drops down to 0. So that's wonderful because students see how the computer interacts with the environment. So this is the first approach to see how the sensor works. I have there a small flashlight. Here's something about the program. Here, the code here, you can see that the first thing that we do is to set the highest value there. We will discuss it in some videos next. So we will see how the microbit reads the data from the light sensor and sends the data to the serial monitor. Okay, so let's go to the next slide and see how it works. So here you create your project. This is the MakeCode homepage. The first thing we do is to create a new project. You can have another one created there. It saves your other projects. You start bringing, changing the name, create a new name. Breakbits is our project. So you create that one. And once it's created, you see 2 main blocks there, on start and forever. We begin by working with the forever block. Okay, that's a loop. We will configure the same serial output we used earlier. So you go to advanced, and then you select serial. That's where you see many other options there, but you go to advanced and serial, and you write a new line there that it has a number in it. You can serial write a number. So we will do it. We will put it in a forever loop. You don't need a board to program it. You just can simulate some inputs. So we will put it as an input, a light level there. Okay, and as soon as we place it, we can see some values appearing there, and you can change it into the simulator, like shining a lot of light or not. So it's a lot of data going together, a lot of messy numbers going around, going in the screen. So we have to be clear that we have to do something else. So the values, we can separate it by an empty line to arrange them into a lot of numbers going with like an enter or space there going through. So it's easy to read. Well, next we will create some variables. Have you ever used variables before? Because they are so important. So we will create some values there. The first one is the highest value of light. So we will store the one that is the highest we read and the lowest value. So in the microbit, we will set some values for us a first start. So the lowest value of light is 0. So we will set it to 0. And the highest value of light is 255. That's for default. But in the practice, we will measure it via the serial readings that you have from the environment. So we will create another forever block. So we have now the light level coming through the sensor and some values that you have in the scope. So we will go to a forever block, a new forever block that is in BASIC there. You've seen that. Inside this loop, we will create a new variable called brightness. We want to store the brightness inside a variable. So there, we will store the light level inside there. It's a local variable that we create inside this forever loop. And then we will create another one that will store the note, the sound that we'll be reproducing after that. So this is where the main transformation happens. We will use another function, and hope this is the last function that we'll be using. It's a mapping function that you can find in the math tools. So we will convert the brightness value from its minimum and its maximum range into a new range that will take the values of the sound. Okay, so we take the brightness, we map the brightness from the lowest value and to the highest value we configured before. We take it, we make our program well done because we are using variables, and then we will set the lowest value of sound and then the highest value of sound that we'll be using. We will be using 440 hertz. That is also known the La sound. So it means that each level we translate into a musical pitch. So the note will not play itself. We can read the variable. The microbit has the ability to reproduce the values for itself. You have to go to music. It has a piezoelectric. The new version of the microbit has a small piezoelectric inside there. And then we will play this note via the variable we generated. So what they're using there is like we go to variables, we take the note, and we reproduce the value of the note for half a bit. You can try another tempos, but that one sounds very great. So you will change it and you will see how it sounds. Now we are using a simulator. Now you will see the real simulation that will show the result of this program. So there you are. We'll play that and see. It's very loud. Sorry for the sound, but it's very loud. So, sorry for this noise, but you went into a workshop or something that is a sound transceiver. So here you have this piece electric that's the magic and sounds pretty good. So there you have a translation between light and sound. So let's go to the next step. So we have to build a light-sensitive musical housing, a synthesizer housing. The students will they will adopt a maker mindset. Okay, they will design an enclosure that controls how light passes through the image strip that you had. So they will experimenting with shapes, openings, and materials. They will improve how accurately the system distinguish between light variations. So this process will help them to redefine the sound output, creating smoother and more meaningful RGS responses. So the key thing here is iteration. They will create one project, they will encourage some problems, and they will create a functional design. So in the next slide, you can see some prototypes. There are one of my students, and there is another solution there created. Then they can create a big box or a small box to create the same solution. There is no right solution there. It's the iteration process and the engineering process that they go through that are rich. So they will define the problem, create a solution, they will test it, and they will be making improvements. So the focus here is not the perfection, but the iteration to learn through the design. So who wants to see testing? Because we have seen how the light changed the sound, but we have to see how the stripe, when you move slowly through the system, read the changes of light. We'll make some smoother, some variations, and like we've seen before, we saw that we have a little scope that you can change into the lowest value of light and the highest value of light. So you can create a wide range of sounds created by these different strips. So you can move it faster or slower, and you will see changes, like in this video. So there you have the light. We have created an enclosure made for this light. Here you move the strip through the device, and now you put it in front of the microbit, in front of the sensor. So as the strip moves, you can see different variations into the sound. So the string, you have to pull the strip and generate different sounds around this box. I mean, you can make a lot of changes. You can add, for example, some light filters to it. You can generate different patterns. That's on your students. That's an idea. That's something you can change into the conception of the device. The students will lead the project. So before moving forward, it's important to mention a key technical limitation of the microbit. The microbit uses the LED matrix not only as a display. Okay, you have here the LED matrix not only as a display, but also as a light sensor. However, it does not measure light on each LED individually. Instead, the board calculates an average light value from the entire LED matrix. This means that light and dark areas across the image are combined into a single overall value. So when we move the strip, the system is reading an average of grays and highlights and shadows rather than analyzing each pixel separately. Okay, so this works well for interesting the concept, but also defines the limit of the microbit, what microbit can do. So that's where Katie will show you how to use other technologies that can be used to analyze images in a pixel level, allowing each part of the image to be measured individually. Thank you, Katie.
Great. Thank you so much, Martin, for that incredible demonstration of the microbit activity. So that was part one of the Bright Beats challenge. And now we'll go on to demoing the second part. In this second part, students will switch to MATLAB to create a digital synthesizer that builds upon their microbit device. So far, students have built a microbit device that can translate ambient light into sounds. And as Martin said, this is a great introduction to sensors and signals. Students will learn how a simple light sensor can detect big changes in brightness and convert those into musical notes. But as Martin mentioned, the microbit does have its limitations. It can only detect overall brightness in very high contrast images, but it can't detect fine details or colors. It can give us a single number for light intensity as an average over a small image area. And that's great for simple patterns, but not so great for complex images. But now we can take the foundation that we've built with our microbit device and amplify it using MATLAB, a powerful computational tool that's used by engineers and scientists for real-world applications of signal processing. MATLAB lets us represent an image as a matrix of thousands of pixels, each with its own brightness or color value. This means that with MATLAB, students can explore more complex images. They can apply signal processing techniques like smoothing and sampling, and they can further customize the sounds that are generated because they'll have full access to edit the underlying code, unlike in the MakeCode IDE that Martin gave you a demonstration of earlier. And most importantly, MATLAB is an industry standard tool used by millions of scientists and engineers around the world for its signal processing capabilities across industries like automotive, aerospace, medical devices, communications, neuroscience, and industrial machinery. So this MATLAB activity can provide your students with an authentic experience of using the same tools that are used by professionals to manipulate and interpret signals. Throughout the MATLAB activity, students will use MATLAB to transform pixels from digital images into piano notes, starting with simple black and white stripes, then moving on to more detailed grayscale images, and finally onto color images. And along the way, students will define and apply key image and signal processing concepts like pixels, smoothing, and sampling. In today's webinar, I'm going to provide a quick demo of how you can access the MATLAB activity from tryengineering.org and provide a brief overview of the sequence of MATLAB activities. Today, we're going to focus mostly on part 2. So please note that this demo highlights only a few aspects of the MATLAB activity, and we really hope you'll take some time to explore the activity more deeply on your own. So starting off, from the lesson plan on tryengineering.org, you can travel straight to the MATLAB activity page to access the necessary MATLAB files. From here, you can simply click the button Open in MATLAB Online to open the activity directly in a browser window. Once you save the folder to your MATLAB drive, you can either navigate to the instructor guide to view some background knowledge and tips and tricks for implementation, or you can open the student activity directly. The first thing that I want to mention is that this document is in the form of what we call a live script, which means that it's an interactive document that combines MATLAB code with formatted text and easy to use interactive controls, which I'll demonstrate shortly. You'll also notice at the top that there are some embedded links to help you jump to different parts of the activity. And most importantly, you can toggle between views to either hide the code or to display the underlying MATLAB code. This allows you and interested students to choose how you want to interact with this activity. You can either use the built-in controls, or you could even manipulate and edit the underlying code. Students will therefore have the opportunity to explore the code as much as they want, and you as the instructor can customize the activity for your use. Moving now into a demo of the lesson. To get started, students will first choose a range of piano notes to use for the activity. You'll notice that when I use an interactive button, it deploys the underlying code. The next interactive button here generates a simple black and white striped image. So for this first MATLAB activity, students are starting with a very simple image. From there, you can use MATLAB to generate a plot of the brightness of the stripes. And again, this simple black and white image mirrors the high contrast black and white drawings the students just used for their microbit activity. So it provides a bit of a bridge between the two parts. Next, we can use MATLAB to translate the brightness values into sounds, with the black stripe being represented by the lowest notes and the white stripes represented by the highest. And you'll notice that as each sound is played, a red dot appeared to indicate which stripe the note corresponded to. Within the MATLAB live script, you'll also find some hands-on interactive challenge ideas that can help you reinforce key concepts. For example, you can challenge your students to try to visualize the striped image just by listening to the sounds, reinforcing that we're transforming a visual signal into an audio one. And we're really testing whether that audio signal can adequately represent visual information. You can also bridge the MATLAB and microbit activities by having students recreate that striped image that was generated in MATLAB and actually pull that through their microbit device. This could provide a great opportunity to compare and contrast how different devices interpret and transform visual information. In the second part of the MATLAB activity, students are progressing to translating a more complex grayscale image into sounds. And for this, students can use any image that they'd like. They can upload an image from their computer, load an example image, or even take a selfie with their webcam. And you can really encourage your students to get creative here. For example, if you wanted to reinforce the connection with their microbit device, you could even have them take a picture of the drawing that they used for their microbit device, upload it to their computer, and use it in this activity. But for the purpose of this demo, I'm going to load one of the example images. And a fun fact here is that the two cat example images are actually of my own two cats. This first one here is of my older cat. His name is Finn. And the second cat example is my younger cat, whose name is Momo. So first, we're going to use MATLAB to convert this image into grayscale. Next, we're going to pick a row of pixels from within the image, and we'll be plotting the brightness values of the pixels along the row that we select. Then this is just like how in the microbit activity, students cut their images into strips. Picking a row from this digital image is just like cutting a strip out of it. Next, we can plot the brightness values of the pixels in our selected row. Since our image has varying shades of gray rather than just being black and white, we now have a range of brightness values from 0 to 1. And this is a super rich brightness signal that we can now manipulate using some common signal processing techniques. For example, students can explore how smoothing affects the brightness signal by toggling between different amounts of smoothing to apply and seeing how it affects the signal. We can also explore the concept of a sampling period. Although this signal represents the brightness of every pixel along our image row, we can encourage our students to question whether it actually makes sense to translate every single pixel into a sound. And by experimenting with these different sampling periods, students can test for themselves the balance between saving computing time and creating a meaningful audio representation of the visual signal. Finally, in part 3, students will actually switch to using the colors of the pixels rather than their brightness to transform the visual signal into an audio one by choosing piano notes to represent different colors. Again, this live script contains different challenge ideas that will help you encourage your students to bridge the connection with the microbit activity, as well as reflect on the real world application of being able to translate visual signals into sounds. Finally, at the very end of this live script, you'll find a list of resources for you and interested students to explore MATLAB and signal processing techniques further. So we hope that this quick preview of the MATLAB activity inspires you to explore the lesson further on your own. We encourage you to play around with it and adapt it to fit your students' interests. That wraps up our demo of the Brightbeats Challenge. We hope that this was a fun and informative way to help you introduce your students to signal processing, both through a hands-on design challenge, as well as an authentic coding and signal processing activity. As a reminder, in the Microbit Design Challenge, students first get a hands-on introduction to the transformation of visual signals into audio signals, but they're limited to simple high-contrast images. With the accompanying MATLAB activity, students are able to use this powerful computational tool to transform increasingly complex images into sounds, starting with that simple black and white striped image, moving to detailed grayscale images, and then finally into color. And they'll be able to use authentic signal processing techniques along the way. So with that, I want to thank Donna and Martin and everyone at IEEE TryEngineering and IEEE Signal Processing Society for this opportunity and this exciting collaboration. At MathWorks, we're so excited to keep growing this collaboration and continue to bring engineering education resources to more students and educators around the world.
Thank you so much, Kathy and Martin, for the wonderful presentations. Oh, thank you so much, Kathy and Martin, for your wonderful presentations. Before we transition to some Q&A, we have a final quick poll for you. Let's see. Great. Please tell us if you will be using this lesson with any school-age children. Thank you so much. Oh, wonderful. Excellent. Thank you so much. We saw quite a few people. Close to 70% will be trying this out with some children. So we're super excited about that. Excellent. Let us look at some questions. I did see some questions for both of you. Let me see here. I'm going to pop some up on the stage. Okay, the first one. Is it possible to do a mapping, not to sound, but to video?
Thank you so much, Andres, for the question. Martin, you can correct me if I'm wrong, but I don't think the microbit has the capability to do videos, but MATLAB does. So yes, in the MATLAB code that you can look at, again, if you toggle under the hood to look at the code underlying the live script, you can pick out the lines of code that map the brightness signals to sounds, and you could convert that to then translating a sound to a certain video. Like you could code that a certain brightness signal will then trigger a certain video to play. And MATLAB does have the capability to play videos. So that's definitely something you could explore in the MATLAB activity.
Excellent. So another question, what age group is the Brightbeats Challenge primarily designed for?
Well, maybe that's on me. I think that this challenge can be used with secondary school students and primary school students. What you have to think is how to adapt certain content of this guide. I mean, you can recycle some certain parts to teach, for example, 7 years old students, like I've done before. I mean, I've been working with a 7-year-old kid with that challenge. He was amazed how you can translate image into sound, and he was more like to build something for the microbit, a little case for the microbit, and he tried to do something with iteration. He created another project, and that's the core part of it. Then you can explain how this system works, but not showing all the code stuff that has from behind. For sure, you can use all the guide with teenagers, for example. So yes, it can be used for children's, but but with certain adaptations.
Great. Great. So I did see this was already answered, but I thought it was worthy of popping up. Can this be done on an iPad, or does this need to be on a laptop?
That's a great question. You can access, I believe, the MakeCode IDE to program the microbit. You can access from an iPad. For the MATLAB activity, there's actually a MATLAB mobile app that you can download from your app store. And then from there, you can log into your MathWorks account and then access your MATLAB drive. So if you have the activity files saved to your MATLAB drive, you can access them from the MATLAB mobile app on your iPad and complete the activity from there.
Excellent. Excellent. So how can we get MathWorks and Simulink license for high school students?
That's a great question. I'm going to pop a link into the chat. Here at MathWorks, we have what we call the primary and secondary school license. This license is priced at $499 USD, and it comes with unlimited seats for all of the students in your school. So if you purchase this primary and secondary school license for your school, every student in your school can get access to our software. I'm going to take a second to just pop the link into the chat so you can explore that license option further.
Great. Thanks, Kathy. Here's another one. How easy would the project be expandable for a 2D space, shapes, not limited to the strips? I think that's for you, Martin.
Yeah, I'm thinking it's like, well, you can use images only because of the sensor of the board. As you can see, you only have there the light sensors there in the screen. So it would be difficult, or you have to think about other sensors of your shape. It's not like a CMOS sensor of a camera. It's just a light sensor that can relate the idea of shades, and lights. So you can create some sort of device with a lot of LEDs, making appear some shaded lights in each part. And thinking out loud, a maker idea how you can make this device with more like shapes. Is that the idea of the answer?
Great, great. We have a couple more. Here's one that's, let me look at this one. This one's a little specific. Our section usually buys materials and goes out to schools and helps teach the kids. We have 20 notebooks from current license. It looks like schools can get a license for $500, but would need to pay $149 a notebook. Is this correct?
Great question. So I think what you're getting at here is the software license versus the hardware that you would need for the activity. So the software license, you're correct, is $500 for the school, but this doesn't cover any hardware costs like a notebook.
Great. There's this one, and then there's a comment. We'll add a couple of comments. How can I get the device? I think we're talking about the microbit, Martin.
I think about the Bible, yes. Yeah, I mean, you have a lot of providers in the world, so that's a common question. It depends where you are from. There is obviously it's easier to find a microbit in the UK. That's where the project is from. So if you are from the United Kingdom, you can reach out the microbit people around and ask them which are the local providers. But you can look on the internet. Then there are a lot of microbits in Amazon. If you can get there, maybe a China supplier can be reached. You can watch in all these board specialized in. We are not in any partnership with them, so I don't want to give special names. So, but if you Google it, you will find some place to buy it. Um, Here in Uruguay, we have the luck. I'm from Uruguay, so here in Uruguay we have the luck to have a special government. It's a place that gives us for free if you're a teacher, and that's easier for us. But you can buy it in certain places on the internet.
Great. There's a couple of questions around license. So I'll pop this one up about nonprofits.
Yes, that's a great question, Vendra. There is a license type for nonprofit organizations that do STEM outreach. So I'm going to pop a link in the chat that will take you to the page that provides license information for what we call our STEM outreach license. So the STEM outreach license is available free of charge for qualifying organizations. So in order to qualify, it needs to be a nonprofit and non-degree granting organization. On this website that I just popped into the chat, you'll see a link to an application form that you can fill out to determine if your organization qualifies. There was also a question in the chat from Craig about licenses for IEEE sections that will be using this activity. We are planning to help train some IEEE volunteers through STEM outreach training. And we can also get you access to the STEM outreach license as well. So you can get access to MATLAB and Simulink when you're out there using this particular activity with your groups like Girl Scouts, Boy Scouts, whichever. If you have questions about being able to access MATLAB and Simulink through IEEE STEM outreach volunteering, I would definitely recommend you reach out to myself or to Donna directly, and we'll make sure that you have access for your activities.
Excellent, excellent. Let's see. I know that there was one more that I wanted to pop up, and then one comment, and then we'll have to close because we're up against the clock. Here we've got this one. What are the advantages of using MATLAB over microbit for the simulation?
Oh, great question. Let me just back up a bit. So the microbit device is great because it provides a really awesome hands-on introduction to the idea of being able to transform a visual signal into a sound. But as Martin mentioned, and as I briefly mentioned as well, the microbit's a little bit limited in what kinds of visual information it can interpret. So the light sensor on the microbit is actually embedded in this matrix of LEDs. And what we're doing when we pull this strip across this light sensor grid is the microbit is calculating in average brightness that represents this entire area of the image that's covered by the sensor grid. So you get one average number for one small area of your image. The microbit also can't do colors either. So with MATLAB, we're able to represent images in a lot more detail, and that students can also explore more complex images. So with MATLAB, you can actually represent every single pixel in an image simultaneously as a matrix of either brightness values or RGB color values. And so this allows you to actually transform every single pixel into a musical note if that's what you wanted. And then MATLAB as well, because it is designed for engineers who are doing signal processing, there's a lot of built-in capability and built-in functioning for students to actually use real signal processing techniques on the visual information, like with the smoothing and the sampling period I showed earlier. You can also, with the MATLAB activity that we have, because all of the underlying code is there, your students and you have the opportunity to really explore and customize any part of the code that you might want.
Excellent. Thank you so much. We'll do this one last comment and then we'll close out as we're up against the clock. I just wanted to, I love this comment. This can help pupils develop interest in STEM. Absolutely. That's what we're all about, right? We want to inspire students to consider STEM professions, and we want to develop a diverse and strong STEM workforce. So thank you for that wonderful comment, and thank you everyone for participating. I once again want to thank our wonderful speakers, Kathy and Martin, for sharing their expertise on this Bright Beats challenge. We also want to thank MathWorks and IEEE Signal Processing Society for their collaboration. And I have a special thank you for all of you for joining us today. You will receive an email soon with the slides and a replay link. And we encourage you to stay in contact with us via our TryEngineering newsletter to learn more about any new resources and opportunities that come from these two partnerships and other initiatives. So thank you again, and we hope you have a wonderful day.